Hello, welcome to the fourth live session of Concept Topology 1 NPTEL course. I'm Shovik and I'm working under Tunas partial matrix. So today, so in last live session, we have gone through um, continuous function and all. Okay, so, um, so today we shall start connectedness. Okay. Then we will go with compactness and then we will gradually solve the problems. But first we shall try to finish the theory part as soon as possible. Okay. Okay. So before starting this, there is one concept known as order topology. Okay. I mean, firstly, this order topology is not very useful at all. I mean, it is useful, but it is not too much useful. But anyway, since while solving exercise, we need to learn. So first, it is better to learn the order topology. So first, we'll look into the order topology. Then we shall gradually look into the continuity and all. Okay. Before starting, let me know whether I'm audible and whether the screen is visible to you or not. Am I audible or whether the screen is visible to you or not? Okay, thank you, Vijay. Okay, first, before starting, let me know, do you have any doubt, any question from previous lab session or any question from the assignment? I mean, last week's assignment. Do you have any question? If you have any questions, please ask. Okay, it seems that there is no question here. Okay, today we shall start with order topology. Okay, before starting, okay, right. Okay, so Anjali, I mean, whoever is the meeting, just tell me, let me know. The point is that while looking the screen, I can't see the chat actually. For looking the chat, I need to change the screen. So that's why if you have any question or any doubt, or if you want to say anything, please unmute yourself and speak. Okay. So Anjali, can you tell me what does it mean by inverse image? I mean, I know inverse image means some if inverse singular and y. So I mean, but for practice problems involving inverse image, what does it mean? I mean, I can't get you actually properly. As far I understand, the inverse image means if inverse singular y that I said, but actually whatever problem you want, I mean you can write also because I'm looking at the chat now.
Why are we spending so much time on metric spaces?
Sorry.
We're spending a lot of time on metric spaces. I thought this was a course in topology.
Yeah, but yes, it was. Yes, it's a course in topology, but I did not spend time in a metric space, right? As far I can remember, correct? Yeah, I mean, I had not spent many much time in metric. So possibly the Sastry side has spent a sufficient amount of time in metric space. But the thing is that the problem is that the problem is that most of the situation it happens that first students go through the real analysis, then they dive into the topology. So in between there is no connection. So that's why possibly Sastry has introduced metric space in the topology course. Okay, that's the only reason.
Okay.
Yeah, but as
I mean,
for
because
yeah, please tell me.
it's
Yeah, please
more
continue.
it's more real analysis and functional analysis. I mean, like
Yeah,
contraction mapping is sort of functional analysis.
yeah, I know, I understand. Okay.
And
That's okay. That's not a problem. I mean, anyway, I mean, if you know the subject, then it's not a it's good to learn things again and again. No, so it's not a problem actually, right?
I want to get away from the real line and get into like abstract
Yeah,
topological spaces.
that's okay. But yeah, but in most no, not only Shastri sir, in most of the colleges, university also, in the topology course, we have the metric space. Okay, so this is it in there actually. That's what it is.
All right. Um,
One
no, I have some questions.
Okay. So, mm, yes, okay. Anjali, can you please tell what does it mean by inverse image problem? I don't get it properly.
Inverse image. What?
Yeah, she wrote like inverse image problem in the chat. Now I don't get it actually. What does it mean? So, are you talking about inverse function? I mean, there is some inverse function theorem in metric is also. Are you talking about that? Because right now, only I can think about that actually.
Are you talking about the homework?
That I don't know actually.
Are you talking about the homework?
Okay. So, mm, one second. Where is okay. Okay. So let's start with the order topology. Okay. Sorry. Hmm. So, okay. So if you consider the real line or natural number, whatever it is, so there is a certain relation. Like if I take any two numbers a and b from this, or a not equal to b, then either a is less than b or a is greater than b. Okay. So this type of relation is known as order relation, and the generalized definition goes as follows. Wait, let me explain very different clearly first. One second. So suppose let A be a non-empty set. Then a relation C on A is said to be an order relation if the following holds. Okay, just tell me one thing. Am I clearly audible? Because in my mic there is some noise actually. Am I audible clearly? Okay, I hope so. Okay, so let's see. We have some non-implicit A and we have some relation C on A. Then C is said to be an order relation of the following holds. For any x and y belongs to A with x not equal to y, then x then either x comma y belongs to C or x comma y doesn't belongs to C. Second property is that for any x belong to A, x comma x does not belong to C. Third relation, if x y belongs to C and y z belongs to C, then x z belongs to C. So this is what the order relation means. So I mean, so if we translate the whole definition in our okay, I hope this size is fine. No, yeah. If we translate the definition in our real line case, so in case of C, we simply consider less than and then these three relation hold. So basically, these three conditions comes from the generalization of the less than or whatever it is. I mean, the natural sense gives these three following properties. Okay, if these three following properties holds, then the relation C is said to be an order relation, and the set capital A is said to be an ordered set. Okay, so this is what we mean by ordered set. Now, order topology D is defined on an ordered set. Okay, so the definition of order topology goes as follows. Once, yeah. Let X non-empty be an ordered set with order less than star. Then we can define the following four things in any ordered set. Open AB contains all those x belongs to x such that A less than x less than B. Open A closed B all contains all those x belongs to x such that A less than x less than equal to B. Closed A open B contains all x belongs to x such that A less than equal to x less than B. Closed A belongs to all x belongs to x so the A less than equal to A or less than equal to A. Okay. So this is the four type of intervals that we can give in order set in a very natural way. And yeah. Now the definition goes as follows. So we have x an ordered set. Okay. Now let beta be the collection of all sets of the following thing. One is all open intervals. Open AB in X. Two is all intervals of the form closed A naught, open B in X, where A naught is the smallest element. Third is all interval of the form open A closed B naught in X, or B naught is largest element if. So what we have? We have some ordered set A and we have some beta, which is collection of the sets of the following type. Firstly, all possible open intervals. Secondly, all possible half closed intervals, and the left side is closed A naught. For A naught is the smallest element if any. Now here this smallest element words make sense because if X is ordered set, so there is possibility of having a smallest set, right? Similarly, if it has a closed, if it has a largest element, then all half open intervals or the form open closed B naught, or B naught the largest element. Okay. So also beta be the collection of all possible sets. Now, um, the topology. No, sorry. Firstly, so we have this collection beta. The thing is that beta is a basis of X, and the topology generated by beta is called order topology. So this is what we mean by order topology. So for the order topology, what we need to have first we have a some non-empty ordered set, and there is a collection beta having all possible open intervals, having all possible half closed intervals, where the left side is start with the smallest element if any, and all possible half closed intervals, where the right side start with open a close, right side end with closed B naught, high B naught largest element. Now one can check that this collection beta forms a basis of X, and the topology generated by beta is called order topology. So this is what we mean by order topology. Okay. So since beta is the basis, so once again, what? Okay, sorry. Yeah, since beta is a basis, so any open, I mean, so in order topology, if you take any point and any open set containing that point, so it will belong to I mean in between. So in between there is a basis element contained inside it. Okay, so this is what the order topology means. Okay, so that's it. There is nothing, not nothing to say. So for example, if we take x equal to r with usual ordering, if we take x equal to r with usual ordering, then I mean, so in that case, it has no empty set. I mean, it has, sorry, it has no smallest element, it has no largest element. Of, okay. So the only, so beta contain only elements of the form open A, and the topology generated by this beta is called order topology in our with the usual ordering. But this type of sets is actually basis for the usual topology. So in real line, order topology coincides with the usual topology. Okay. Why? Because in real line case, we don't have any A naught, which is largest, or we don't have any B naught, which is smallest. So in this case, the base element contain all possible only open intervals. Okay, so that's why it's generated the usual topology. Okay. Okay, so there are some examples which tells that, I mean, so in real line case, order topology, usual topology both coincide, but there are some examples where we will see that in general these are of course different. But right now we are not getting into it. We will look into after, possibly after next week. Right now, now we shall start with um, we shall start with connectedness. Once. Okay. So um, let's start connectedness now. For first, before going to the formal definition and all, let me try to give um, some feeling about connectedness. Okay. So uh, suppose this is real line R. Okay. So this is the real line. So left side, right side is infinite. So in anyway, it is naturally connected because there is no, I mean, it is connected in an obvious way because there is no disconnection or there is no gap. But if we remove one point, then we will get something like this. So this is R minus 0, suppose say. So this is disconnected. Why? Because there is a disconnection. Similarly, if we consider the Euclidean plane, that is R2, there is a whole plane if you consider. It is connected because there is no disconnection. But also if you consider R2 minus 0, simply this, sorry, yeah. If you consider R2 minus 0, only this 0 point will vanish. But anyway, there is no disconnection because if we consider one point and if we take another point, we can go one point to another point, right, directly without doing any match. Okay. So I mean, in that way, there is no disconnection. So I mean, though if we remove single point from real line, it is connected. But in R2 case, if we remove one point from R2, it is also connected. It remains connected. Okay. So I mean, this is the intuition, like something is connected or not. Like we can go directly from one point to another point, or we can move a pencil from one point to another point without pulling up it deep. Okay. So similarly, for example, consider hyperbola. It is of course disconnected because we can't move from one part to another part without pulling up the nib of pen. Okay. But if you consider the parabola, it is of course connected. So this is the form, this is the intuitive definition. Okay. but proper mathematical definition goes as follows. So let X be a topological space. So first, uh, yeah, let X be a topological space. A separation or disconnection is a pair U of disjoint, non-empty, open subset of X whose union is X. And a space is said to be connected if it has no disconnection or separation. So let's try to understand what does this mean. So first we need to understand what does it mean by separation or a disconnection. Separation or disconnection means we can write X as union of two sets U and V which are both disjoint and of course UV non-empty and UV are both open. Then the space is said to be then this pair U comma V said to be a separation. And if the space X has no separation, then it is said to be connected space. Okay. So let's try to connect our intuition with the definition right now. Okay. So so consider R minus 0. Okay. Look, intuitively disconnected. But how to prove it? So in order to show something disconnected means we need to show it has a separation, right? So we need to write R minus 0 as the union of U and V, where U V satisfies those properties. So we can write R minus 0 is equal to minus infinity comma 0 union 0 comma open infinity. This thing is open. This open 0 comma infinity is also open, and their intersection is empty. Hence, R minus 0 has a separation. So it is disconnected. So it is not connected. One second. So let me repeat that one. So we have R minus 0. Okay. So look, R minus 0 is minus infinity comma 0 union 0 comma infinity, both open. Okay. This R minus 0 has separation. Means what? We need to show we can write R minus 0 as the union of U and V having satisfied those properties. Now look, R minus 0 is obviously this thing, this union this, and their intersection is empty. So and both are open. So r minus 0 is not connected. So this is the argument. So I mean, so of course this matches. I mean, this definition matches with the intuition. Do you understand?
Okay.
Yes, sir.
Yeah. Yeah. Okay. So okay. So hmm. So suppose R2 minus suppose consider R2 minus x-axis. So this R2 and this thing our x-axis. So the similar argument tells that R2 minus z x axis has a separation. Why? Because this is one part and this is another part. Take this u and take this v, and clearly u v are both open in R2 and all. So that's why R2 minus x has separation. That's why it's not connected. Okay, but um, but okay, but look, R2 minus x axis is not connected, but R2 minus singleton 0 means only this middle point is not here, but it is connected. But right now it is slightly difficult. After some theorems it is possible to prove there are two minus point is connected, but anyway it is intuitively very much clear that it has to be connected. There is no there, I mean R2 minus 0 can't admit in this connection. It is almost obvious, right? So in that way right now remember it, after some theorems we will see this. Okay. Okay. So this is one definition of, I mean, this is a one definition of connectedness, that is space is said to be connected if has no disconnection or separation. So there is another equivalent definition of connectedness. This goes as follows: a space X is connected if and only if the only subsets of X that are both open and closed in X are empty and exists. So this is another definition. So a space will be connected if and only if, is an if and only statement. The only subsets of X which are both open as well as closed are empty set and X itself. Okay. So can you please try to prove the equivalence between this definition and the previous definition? Take your time. Please try to prove the equivalence of this definition with the previous one. Okay. It is not difficult. So what you need to do? So suppose in the previous definition we have one definition connectedness. Now we need to show this will hold. So you need to start with some non-empty state which is both open and closed but not equal to empty, not equal to X itself. Now you need to derive the contradiction. So try to show the equivalence of these two definitions. Okay. You can take your time. I shall be back after some minutes. Okay. Please think about it.
So, the forward direction we can prove using contradiction. So, we can assume that the space X is connected, and we can say that suppose there exists a non-empty proper subset of X, which is both open and closed. Then, because the set will be open, its complement is closed, and because it's closed, its complement is again open. So we have produced two sets which are open and
Hello,
disjoint. So
hello.
they, yeah,
Yeah, can you please repeat? I was not here.
yeah,
It started, so yeah, please repeat.
yeah. So I was saying that we can prove this the forward direction by contradiction.
Mm-hmm.
So if we assume that the space, if we assume that X is connected, and let us take a non-empty proper subset of X, which is both open and closed, then say the set is uh, some T. So it's because it is closed, then its complement is open, and if, so the complement would be simply X minus A or D.
Mm-hmm.
Yeah. So we have successfully produced two sets, the set and its complement, which are both open and closed in the space, which would form a separation for this. But we have assumed that the space is connected. So this leads to the contradiction.
Correct, correct. Very good. Right. And what about the reverse direction? Think about for the reverse direction. Take your time. But reverse direction is also easy, but just solve it right now. That's what I'm saying. It will hardly have 2 3 minutes. Try to do it by. You can take your time. So for the reverse direction, what you need to check. So you need to assume the fact that it has no x. I mean, a only set of the both open and closed except empty at phi, and you need to check that x can't have any separation. So assume that x has any separation and try to give some kind of contradiction also. I mean, whatever you, no problem. So try think about it.
So,
Yeah.
all right. So if you have a subset A, right, and its closure is not equal to the whole space X, right,
Yes.
then the closure of A is a proper subset of X.
Yes. Correct.
And the same thing for X minus A, that's a proper subset of X. So their intersection has to be empty because they can't both be closed. And
Correct. Correct. Right. Yeah. So that's correct. So okay. So okay. So till now we have seen two definitions of connectedness. So there is another one more definition, but right now we're not getting into this because most probably these two definition will wait. I shall be back after 1 minute. জলটা গরম করে দাও তো। হ্যাঁ yeah. So okay, so most probably these two definition will suffice as the most what if necessary, then we look into the third definition in future. Okay. So okay, so okay, so there is one important lemma in connectedness which is actually very much useful while solving problem. So okay, let me write this statement first. If the set C and D form a separation of X, and if Y is connected, then Y lies entirely within Cn. Okay. So I mean, what does it mean? It is some it is some obvious, right? So like we have some separation C and some D, and this is the whole of X, and so Y is connected means this is Y. So I mean, either Y lies here or Y lies here. But if Y lies something this, then of course this part and this part will constitute separation of Y. So this is what it's saying. If it has if this given space has separation, and if subspace is connected, so it lies entirely within one of its separation. Okay. So how to prove this? Can you anybody please try? I mean, it is actually. I mean, it is very easy. Just it's a use of definition. You please try. If you are not able to solve it, then I will give the solution. Okay. But please first try it yourself. Any idea how to proceed? Okay, look, this is a direct application of definition of it. Okay, and so what you need to start the contradiction. So let Y intersection C non-empty and also Y intersection in non-empty. Okay. So Y can be written as Y intersection C union Y intersection D. Okay. Now C and D are separation. So C and D are open in X. So C intersection Y, D intersection Y are open in Y. So this implies what? This pair Y intersection, this pair Y intersection D forms a separation of Y. So this means what? This means Y is disconnected, right? But it is given that Y is connected. So either Y intersection CMD means Y lies entirely in C, or Y intersection in Y intersection C is empty, that is Y lies entirely in D, or Y intersection D empty, this means Y lies entirely in C. Okay. So do you understand the proof? Okay. 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 So the question. Okay. So let me
You
repeat.
mean
Yeah. The
you mean
question is,
C,
yeah. Suppose we have two sets. I mean, suppose X is a space. Okay. And suppose the sets C and D forms a separation of X. Okay. So C and D separation of X means what? X can be written as union of X can be written as union of C and D, but C and D are both open and their intersection is empty, and their union is the whole of X. Okay, and Y is a connected subspace. Now the question is that, Y is a connected subspace. I'm extremely sorry. Y is a connected subspace. Now the question is that Y lies entirely in C or Y lies entirely in D. Okay. So what we do? We assume that Y intersection C non-empty, Y intersection D non and both non-empty. Now clearly Y can be written as Y intersection C union Y intersection D. Okay. So now C and D are separation. So C and D are both open in A. So C intersection Y, D intersection Y are open in Y. So Y is disconnected. Okay. So this is the contradiction, because in the question it is mentioned that Y is connected. Okay. So that's why either Y intersection empty or Y intersection D. So this is the argument. So now do you understand the argument?
Yes, sir.
Yeah, fine. Okay. So yeah, okay. So
you mean
yeah.
you mean that Y if Y is connected you wrote and. Did you mean or? You
Sorry.
wrote
Please repeat.
Y if Y is connected, Y will lie entirely within you wrote
Yeah.
C and D. Don't you mean C or D?
Yes, correct. So if it is connected, it will lie inside one of its separation. It cannot lie inside both.
Yeah. You wrote and, so you wrote C and D.
No. It is not. I mean, so that's what. Yeah, that's why I wrote.
You wrote
Oh,
C
sorry. Oh, sorry. I'm extremely sorry.
or. I think you meant or.
Yeah, it is all. Yeah,
Yeah.
it
Okay.
is your. Thank you. Thank you. Okay. Okay.
It's okay.
So there is our next theorem, which tells that, yeah, this theorem tells that, this theorem tells that union of connected subspace of X having non-empty intersection So what is the theorem? This theorem is that union of connected subspace of X having no named intersection is connected. So this means what? Suppose we have A alphas and intersection A alpha node empty, and suppose each A alpha connected, then we need to show that union A alpha is also connected. This is what is this is what we mean. Okay. So, okay. So can you please try like you can start as follows. Like suppose I mean, so okay, so in order to show something currently you need to start with the contradiction in most of the situation. Okay. So what you need can do, so you can assume that this is disconnected. So so now, so union, this thing can be written as C union D, or C and D have those properties. I mean, it's a separation. Now, can you please try something for going further? Please think about it, take your time, but please try to do. I mean, it's not difficult, but just it's an easy exercise actually. Please try it by yourself first, otherwise, I will do it for you. Okay, think about it. I shall be back after some minutes. Okay. So are you able to solve this? Are you
Um,
able to solve
so
this? Yeah.
you could do it like one at a time. Like take over all the all alpha. You take one alpha, right? One particular alpha, and you intersect that with the union of all the other alphas, right? So that has to be non-empty. So there's
Yeah.
no two disjoint sets um, in the collection of
No, no.
the alpha.
Sorry, I don't get you. So what I've said, I mean, so if you take a particular alpha, let's call it alpha naught, then what about A alpha naught?
Yeah, if you intersect that with the union
Yeah,
of
correct.
all the alpha where alpha's not equal to alpha zero, right?
Yeah, correct. Yeah.
You intersect A alpha zero with the union of all the other alpha, A alpha.
I mean, like, no, I mean, that's possible, right? I mean, yeah, I mean, that's possible. So we have many, like, suppose we have this is so we have this many of connected pieces, right? And so they might intersect. They did not intersect, but their intersection is non. That's what we only know, correct? So I mean, A alpha naught I mean, might lie inside A alpha one, might lie inside A alpha two, because here everything connected. So there is no problem of one can may lie inside others. Okay. So I mean, so this argument will not work, right?
You take on the right hand side, you take the union of all the A alpha except for the one on the left. The
Okay, then.
alpha naught, yeah, and you intersect that with A alpha, A alpha naught, right?
Okay, then.
You intersect that with A alpha naught, and so none of those can be empty. So um, there's no set. There's no disjoint sets in the A alpha. There's no no separation because there's always something in the intersection.
No, I mean, no, no. Sorry, sorry. Please repeat.
So you go you take one alpha naught, right?
Yeah, right. Okay.
A alpha naught, and you intersect that with the union of all the other A
Yes,
alpha,
correct. Correct, correct.
and that has a non-empty intersection. So there's no,
A non-empty
and you go over
intersection. So you are saying that non-empty intersection with other alphas, right?
the intersection is non-empty,
Yeah, correct, correct. So from the question itself, then
and you take that all over all the alphas, right, one at a time. The A alpha naught on the left, you just go over. So there can't be any two disjoint sets that are empty. There's no
uh,
two disjoint. Because A alpha naught plus the A alpha for all the alpha not equal to A alpha naught
yes,
is the whole thing.
yes, correct.
There's no intersection that's empty.
No, but no, no. I mean, I mean that's what they already given, right? Intersection of all alphas is non-empty, right? It is given already, correct?
Yeah, but if
So I
you
mean,
pull out one A alpha not A alpha at a time, there's no combination of sets that's disjoint.
Okay, I need to think about the argument actually, right? I couldn't figure out the argument. Anyway, it can be done also as follows. Uh, so, uh, uh, hmm. So let union A alpha is disconnected. So union A alpha can be written as union D. Okay. So now, so A alpha subset of union A alpha, which is C union D. Okay. Now it happens for all alpha. Now since each A alpha connected, so A alpha subset of either C or A alpha is subset of either D. Okay. So here we can start with any particular chosen alpha node. Okay. Now, so I mean now if we take any beta for which is not equal to alpha, then due to same reason A alpha will lie inside C or A beta will lie inside D. Now the problem is that if so I mean so for A alpha not either A alpha not subset of C or A alpha not subset of D. So suppose this happens without loss of generality. Okay. So in the case of beta, if A beta subset of D, then A alpha naught intersection A beta is empty because the intersection is empty. So A beta has to lie inside C, right? So this implies what? This implies all alpha not equal to alpha naught A alpha subset of C. This implies what? This implies union A alpha all alpha subset of C. And this implies what? This implies D equal to empty. Okay. But what we have started with, we have started union alpha, C union D, and C and D are both separations of union alpha. Separation means each C and D are non-empty. But finally, we are getting that D is empty. So, I mean, so this is the contradiction. So, what we have done? So, once again, yeah. So, yeah. So, what we have done? So, we have started the contradiction writing union alpha is equal to C union D. Okay. Um, then so we started with a particular alpha node. So A alpha node subset of union alpha, which is C union D. So now A alpha node connected. So A alpha node subset of C or A alpha node subset of D. Okay. Now beta is not equal alpha node. So A beta subset of has to be subset of C or A beta subset of D. Now the point is that since the intersection of all A alphas is non-empty, so if A beta lies inside entirely inside D, then the intersection with A alpha naught is empty, but that contradicts the hypothesis of the statement. So if A alpha naught subset of C, then all other A alphas will lie entirely inside C, and this gives that union A alpha is equal to C only. So implies what? Implies D is equal to empty set, right? So this is the contradiction. Do you understand?
Yes, sir.
Okay.
Okay.
Yeah. Fine. Okay. So this means what? A union of arbitrary collection of connected set having a common point is connected. Oh. So now there is another new theorem that how connectedness works in the case of continuous maps. So let f x to y be connected and sorry it has done this. So let f x to y be continuous and let x connected. Then f x is connected. Okay. So this image what? Image of a connected cell and continuous map is also connected. So this is what we mean. Okay. So in order to prove this, you need to start with suppose if it's disconnected and then you need to do okay. So you start with by assuming that if it's disconnected and try to drive a contradiction. Okay, please do it. Try to do it by yourself. It is not difficult at all. Okay, please think and try to solve. You can take your time. If you have found the answer or done with the answer, please let me know.
Okay.
How about
So say you have two sets, H and K.
yeah? Okay.
Okay. You have two sets, H and K, and their union is Y.
No, in just fx not y. It is fx not y. Hmm.
And their union is Y, and their intersection is empty.
Yeah. Then
H intersect. So if you take F inverse of H intersect K, take F inverse, the inverse image of H intersect K, intersect, no, intersect,
uh, no,
inter,
no, this, no, no,
intersect.
this, no, no, fx equal to h unit, fx equal to h unit, right? So what's an
Okay.
I mean, union,
Right.
respects
So
for the
take
inverse,
the
right?
inverse, take the inverse image. Yeah. So f of x is equal to h union k. H intersect k is empty. So
Yeah,
take the image of um, h intersect k, the one on the right.
one minute. Yeah. So if inverse H intersection, if inverse K,
No,
if
h
correct,
f inverse of the whole thing, of the whole intersection.
correct.
Okay? Yeah, well, that's the conclusion. Yeah. If you take
So
f
yeah,
inverse of the whole thing, the whole intersection, h
mhm,
intersect k, then that's equal to the inverse image of each of them, f inverse of each, the two individual sets. And that has to be empty.
correct. Yeah. So anyway, so H and K open. So
So
inverse. So I think now everybody gets how to do it, right? Correct. So yeah, that's good. So okay. So now um, there is another theorem is the following. Just 2 minutes. I should have 2 minutes. Yeah. Okay. So now the next theorem is as follows. That is, if x and y connected, then x plus y is connected. So this is one of the important theorem. Now the point is that this cannot be proved in the contradictory method. Okay, this has to be proved in very direct way. Okay, so for that we need to use some theorem like intersection of arbitrary. I mean, union of arbitrary connected is connected whenever the intersection already. This type of thing we need to use. Okay, and also you need to use that continuous map takes connected sets to connected set. Okay, so let's see how to do this. Okay, but it is not straightforward actually. So okay, so start choose any point x and y. Okay, so and consider any point open. Okay, define Tx to be x cross singleton b cross singleton x cross y. So what is Tx? X cross singleton b means what? This line. Okay, and singleton x cross y means this line. This, the union of these two lines, we are calling it Tx. Okay. Now, of course, now look, this, I mean, this thing is connected x cross singleton b, of course, because x is connected, singleton x cross y is also connected, right? And from the picture, it is clear that this intersection a comma b lies between the intersection of these two, right? So this is similar to what? This similar their union, namely the Tx is connected, right? Now, so what we get see is that this line union this line is connected. Okay. Now, so if we vary x, so this line, so this is x, right? So this line comes from where? This line, yeah, yeah. So this line comes from choosing a small x. So now, if we vary the small x throughout this capital X, then their union will give the whole Tx, right? Correct. So now, clearly Tx1 intersection Tx2 non-empty as open AB belongs to Tx1 intersection Tx2. So union Tx where x belongs to x is connected. So this thing is x cross y. Okay. So that's why the x cross y is connected. So this is the argument. So okay, so let me repeat it. So we have x and y, okay, and both connected. So we choose the first 2 points AB and XY in the x cross y plane, okay, and then we have formed, sorry, this Tx is equal to x cross b union singleton x cross y, okay. Now this thing is connected, this thing singleton x cross y is also connected, their intersection is non-empty. So Tx is connected. So Tx is now this line. So now if we vary the singleton x throughout capital X, then union give x cross y, right? So but sorry intersection of all these Tx where x belongs to x is non-empty as this point AB belongs to Tx for all x belongs to x. So that is why intersection Tx is connected, where union T is connected, where union Tx is nothing but equal to x cross y. Okay. So do you understand the argument? I mean, yeah, it's a bit messy, but it's yeah,
Okay.
yeah, fine. Okay. Yeah. Oh, so so the product and current displays are connected. Okay. So now, okay. Yeah. So there is a very important one of the important theorem for checking the connecting is very easy with the following. A space X is connected once. Let me check the detail once. Oh. So suppose a space X is, space X is connected if and only if any continuous vector G from X to a 2-point set is called as constant. So what is the statement? A space is connected if and only if any continuous map G from X to a doubleton set is always constant. So okay, so can you please try about the one at least one direction? Can you please try for the one direction? So assume that X is connected now. You need to show that the map from X to plus minus 1 is always constant. This direction, can you please prove?
Well, I mean, the forward
Yeah, great,
direction is, it's
great.
pretty obvious.
Yes, it's a good real. It's obvious. Yeah, that's correct. Well, okay, so that's good. But what about convert? Suppose like it satisfies the condition that for any map from X to double dense constant, you need to share that connected space. So for the converts, what to do? Any idea? It is not difficult. It is also easy and pretty obvious too. But do you have any guess how to proceed?
I don't understand.
No, no. For the converse part, suppose it is known that for any given map G from X to plus, for any map G from X to plus minus 1 is continuous, always constant, you need to check that it's connected. So, because it's a if and only statement, right? So, so for the converse part, how to prove? Any idea?
I I don't understand. You're mapping x to plus or minus one,
Yeah, it's always constant. Constant.
so it has to be one or the other.
Yeah, it may be 1 or it may be minus 1. but it's constant. I mean, either one or minus one.
It has to be either plus one or if it's constant.
Sorry.
If it's constant, it has to be one or the other. It
Yeah.
can't be one one on plus one on some parts and minus one on other parts.
Yeah, I mean, either the wholly it will be plus one or wholly it is a minus one. That's what the meaning is, right? So you need to check that basically if x satisfies this property, that any continuous map from x to plus minus one is always constant. You need to check that x is connected. So in order to prove this, I mean, if you assume that x is disconnected, so you need to come up with some continuous function from x to plus minus one, which attains both one, I mean, both plus one and both minus one, right? So you need to consider such a function by assuming that x is disconnected. So how to proceed? Do you understand what we need to do?
Yeah, if x is disconnected, then
Yeah.
it's the union of two disjoint sets, so you can map one to plus one and one to minus one.
Correct. Right. Very nice. And so intersection is empty, so it has so anyway, so from the union this map is continuous, so it is yeah, right. So yeah, that's fine. Okay. So this particular theorem is actually very useful in order to prove something is at least disconnected, because so we may come up we may construct a function from x to plus minus is not constant, so we can directly say that it's just disconnected, right? So that's why the theorem is useful. Okay. So so for the time being, assume that real line is connected. I mean, sorry, it is there is no point of assuming this. So since you already have gone through the real analysis course, so it is expected now you can prove that real line is connected. Okay, you can use any of these three definitions. You can directly prove the real is connected. I am not going the proof because the proof is slightly cumbersome, but it is not difficult. It's actually easy. Please try to do it by yourself. If you have any doubt or if you couldn't solve it by yourself, then ask me the next lab session. But for the timing, assuming that real line is connected, okay. So since real line is connected, so R cross R also connected, right? Because due to the following theorem that x connected y connected x was connected, right? Okay. So so R cross R is connected. So similarly, so go on, and R to the body now also connected. Okay. So by assuming that fact, real line is connected, R to the body is connected for any year. Okay. Now uh, okay. So there is another theorem which we will prove later on. It is tricky actually. So let x and y both connected, and let a and b proper subset of a and b respectively. Then X cross Y minus A cross B. X and Y both connected. Okay. And A and B are proper subs to A and proper subs to X1 rest. Sorry, it is not A and B. Then Y and X2. Proper subset of X and Y respectively. Then the X cross Y minus A cross B is connected. Okay. For the time we assume assume this theorem. Okay. So this theorem gives what? This theorem gives R2 minus singleton 0 connected, right? Similarly, Rn minus singleton point connected, right? So, okay. Now, so what we got? We got R to the power minus 0 is connected. Now, consider function R to the power n minus 0 to Sn minus 1 by the map x goes to x by norm x. So, this is a continuous plus surjective map. Okay. So this gives what? This gives that s to the power n minus 1, that is the n minus 1 sphere is connected. Right? Do you understand what's going on? Because these are the just a consequence of those theorems actually. Okay. So combining all these things gives that s to the power n minus 1, that is, I mean, sorry, the n minus 1 sphere is connected. Okay. And yeah, that's nice. Okay. And okay. And once again. Okay. So these are these small consequences. Okay. So now let's try to do some exercises. Okay. So okay. So prove that GLN are disconnected. So prove that GLN are disconnected means what? So you need to. So I mean, so look. In order to prove something disconnected, it is always better to go with the continuous map approach. That is, you need to construct a map from. I mean, you need to somehow construct a map from GLNR to doubleton set plus minus 1, which is not a constant map. If you can prove the existence of such a map, then automatically this implies that the domain is disconnected, right? So this way you can show many things are disconnected. I mean, it is not usually. It is usually not. It is not practical to go with the definition. You need to use this following theorem. So try to construct a function from GLNR to double turn set plus minus 1, which attains both plus 1 and both minus 1. Okay. Think about it, take your time. And if you're done, please let me know. are able to find such a function from GLN to plus minus 1?
No, sir.
Okay. So, I mean, so, so GLN means what? Contains all matrices with no zero determinant, right? So, the determinant function, take the determinant function, anyway it is continuous. Okay. And this is goes as follows. A goes to
So, but why would determinant of any n by n matrix whose determinant is non-zero only map to plus minus 1? This is not singular linear set of matrices, right?
no, no, I mean, when it is not exactly determinate, the map goes as follows. A goes to plus 1 if, okay, so let me write it down in a more elegant way. One second. Okay, yeah, correct. So A goes to determinant A by more determinant A. And yeah, so this function is a map from GLNR to plus minus 1. Now do you understand?
Yes, sir.
It is not just a determinant, it's determinant by more determinant A. It gives a map from GLNR to plus minus 1 and it has both of its values obviously. I mean, it's surjecting, so that's why GLNR is not connected. That's it. So, okay. So, now, so can you please tell that O in R, the orthogonal matrices is not connected? Can you please tell how? There is an orthogonal matrix is not connected. Can you please tell how? So you need to construct our same function from O in R to plus minus 1, which attains both of its values, right? So what function, what natural function you will choose? What natural function you can choose from Y naught to plus minus one. So easy, I thought you should get it. Anyway, So obviously the same map will work when at plus minus 1, the determinant A goes to determinant. It is in your contrast map and that is both of its values, so it is the winner is not connected. Okay. So okay, so these are some example exercises. So now okay, so now try to show that okay, R with lower limit topology is disconnected. Why? R, I mean real line is lower limit topology disconnected. Why? So now look, since the topology is to disconnect, I mean sorry, it's a lower limit topology. I mean it is something different from usual. So here applying the concept of continuity is quite maybe difficult. Okay, so here better try to get some separation for R with lower limit topology. Okay, so that is you need to write RL with E and V having those properties. Okay, so try to think about and come up with U and V. Okay, do you understand what you need to do? I hope so. Okay, so try to get U and V. Okay, so it is maybe quite tricky. So look, you can write RL as follows. RL can be written as minus infinity open 0 unit close 0 open. This thing is nothing but union of y comma 0 y less than 0, and this thing is nothing but union of 0 comma x x greater than 0. Each of this is open in R with lower limit topology. This also, so their union it is also open. And this is also open. Okay, so as a whole, R with lower limit topology is so. I mean, so this and this constitutes a disconnection of RL. So that's why RL is disconnected. Okay, so this is argument. Do you understand? Do you understand? Let me know.
So what was RL?
Means R with lower limit topology. Can you remember the definition of lower limit topology?
Uh, a lower limit. So lower limit of what?
So, what is the definition of lower limit topology? What is the definition of this? So, okay, so it's it went forward actually. So, okay, so one second. So, R with lower, so the open set. So, R with lower limit to, R with lower limit topology. This is known as the lower limit topology. These open sets, sorry, the basis elements of the form open A closed, sorry, closed open B. This forms a base element. When this forms a base and topology generated by this type of basis is called as the lower limit topology. Okay. Lower limit does not is not essentially meaning in a lower limit. It is the name of the topology, lower limit topology. Okay, means the base element of the form closed A open B. Okay, so this is the definition for the lower limit topology. Now, do you understand?
Yes, sir.
Okay, so okay, so there is one exercise. So let n, sorry, be a sequence of connected subspace of X such that A intersection n plus 1 non-empty for all n. Show that union n is connected. So an is a sequence of connected subspace such that their consecutive intersection is non-empty. We need to show that their whole union is connected. So how to proceed? So what we need to do? You need to start with a continuous map uni from union a n to plus minus 1, and you need to somehow show that this map is constant. So so this in this way you can only right. So how to do or how to proceed or what should be the argument? Think about it. Take your time. It is not difficult, but it is slightly tricky, of course, but it is not difficult. Hmm. So any idea how to proceed? Okay, it's now 2 hours actually, so I have some work to do. Anyway, so please think about this problem. Okay? If you have any doubt, I mean, please try it by yourself. You need to consider function. For let me start with a function f from union a into plus one. I need to somehow show that this is a constant. Okay, think about it and try to solve. If you are not able to solve it, please ask me the next session. Okay. 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 So let's stop here. Okay. So we'll meet in next week. Okay. Okay. So I'm leaving the session. Also, one more thing, mainly mark your attendance by submitting the Google form that I have already shared in chat. Just now I have shared the Google form in chat. Please mark your attendance. After doing, please let me know. After marking attendance, please let me know. Okay, I have some another thing. I have a meeting to attend, so I'm leaving the call. Please mark your attendance. Okay. Anyway, so leaving the call.